Hello, I'm Vlad, and I'm very glad to present polyatomic crystals. Okay, now it works. We start with a perovskite structure as it's one of the simplest one, and you can see on the subplot A that in the middle you have a bulky, which means a big A metal cation, and in the corners you have B-type metal cation, which is smaller, and in between you have oxygen. Although it is shown as a small ball, actually this is one of the largest atoms in that cell, and together with the green one, the oxygen atoms determine the packing of that structure. And within that packing, into the octahedral, no, it's a cubic, into the cubic hole, you put the atom A. The rest of the atoms, which are B-type, they are situated in the octahedral holes made by oxygen atoms. And this is a very nice illustration of various types of holes in solids. So let me remind you that there is tetrahedral, where you have 4 atoms, and in between them you put your second atom. Then you have octahedral coordination like presented here, where you have 6 oxygen atoms, and in the hole between them you put a cation. And finally you have a cubic hole between 4 atoms, where you put inside the second atom. The perovskite structure is the close-packed structure, which means that there is an ideal ratio of radiuses, and of course you can use the Pythagoras theorem to show that when the sum of Ri and Ro divided by Rb plus Ro equals to square root of 2, then actually all the atoms in your structure, they touch each other, they form close packed structure with a geometry of perovskite. And for the first time, this type of structure appeared in the preparatory problems in 2017. You were given the unit cell with some atom in the center. You are given the formula and you are asked to derive the structure. There were some hints, but now we can actually go without those hints just by considering the following most important concept when we are talking about unit cells and close packing. And this concept says that when we have this simple cubic, the atoms in the corner are actually shared with 8 other unit cells, and therefore each atom in the corner is actually presented within our unit cell as 1/8 of an atom. However, because we have 8 corners, we multiplied 8 by 1 divided by 8, and we get 1 atom within the simple cubic packing. Let me stress it again. When you see an atom in a corner in a cubic cell like this, then you must count it as 1/8. That is a basic concept, and we go through it so you don't make a mistake when the time comes. The body-centered cubic is even simpler. You can see that now we have some atoms in the corners and we have one atom in the middle, which is not shared with any other unit cell, and therefore it is just one atom and we can count it easily. And whenever we have any kind of atom within unit cell, doesn't matter how complex it is, but we clearly see that it is in the unit cell and it is not shared anyhow with other units around, then it counts as a single unit. And finally, here is a simple example of face-centered cubic packing, where some of the atoms are situated in the middle of a face, which means that they are divided by 2 between 2 unit cells which share the same face here, right? And then you just count how many faces has a cube, 6, and you multiply 6 by 1/2, and you get 3 atoms which are situated at the faces. And that's it for the face-centered cubic packing. We have in total 4 atoms in the unit cell. Now, there is not shown one example which imply that you have an atom at the edge of your cube, somewhere here. I hope you can see my mouse. Then it will be divided by, now I'm giving you 3 seconds to think how many unit cells around, and the answer is 4, and therefore it is 1/4. And you just count how many edges a cube has, and you get the number 12. So 12 multiplied by 1/4 give you how many? 3 atoms. Then, as you can see, the composition is titanium O3. So okay, so it's not a mistake, but that's actually, now I understand that is a very interesting question. So you must think, where would you like to put your oxygens? Because if you put them into if you center them at faces, then you will have 3 oxygen atoms. But you can also put them at the edge, and in total you will still have 3 oxygen atoms. Okay, so it's not a mistake, it's a very interesting question with a trick here, because you must now think whether you put oxygens on the edges, and in this case the titanium atom will be in the octahedral hole. But if you put oxygen atoms in the middle of each face, then what would be the coordination of titanium? Octahedral, right? And that is actually chemically correct. So in this problem, we must put oxygens in the middle of each face, and then we put strontium here in the corner, which actually means that it will have a place in a cubic hole. So I'm not showing that answer here, but I hope you can take a pen right now and draw it yourself. What I'm showing is another type of structure. I've put it as an answer, but in that case it is wrong here, because again, you should put oxygens for this specific question, considering that titanium is in the center, it is the smallest ion here, so it must be in octahedral hole, and therefore we put oxygens into the middle of each face and strontium in the corner. Now this is an answer to another kind of perovskite structure, where you have kind of organic cation and you have iodide of lead. And this is mentioned in the preparatory problem 22, but the structure is not shown. And again, because this organic cation is the largest one, it will be in the largest hole, which is cubic one. And the rest, like lead iodide, is here forming octahedrons. Now let's go to some other structures, which are Spinel structures. I think that is one of the best representations what you have here. The A is a whole structure, and then we can divide it into 2 parts. One with tetrahedral holes and another one with octahedral holes. And now you can see that this group here is forming a tetrahedron of octahedrons. And then again, this formation forms a tetrahedron of tetrahedrons of octahedrons. Now that might be difficult to understand, that, but just if you take some time and look into that picture, you might see it. Again, what I'm saying here is, of course you can see octahedron, but then you mark that 4 of them are sharing some faces and they form a tetrahedron unit. And then within the unit cell, there are 4 units like this, and they are situated in the corners opposite to each other in the unit cell, and therefore it's actually another tetrahedron structure. So just sounds quite funny. It's a octahedron of tetrahedron, and I hope that I put logic here in correct way. So that's it. And if we take a look on the other structure, it is actually much simpler, because we have tetrahedrons, and they form, first of all, the face-centered packing. As you can see, you definitely mark them in the corners, and then you can definitely see that they are occupying middle of each face. And finally, you can also see that they are taking those tetrahedron holes between tetrahedrons, like here. And overall, if we now put together those structures, we get the normal Spinel structure. Another way to represent it is like this, where we take the same cubic unit cell, but we just show some of the parts of that unit cell. It doesn't mean that you don't have so many atoms. We just focus on 1/8 of this cube and another corner of this cube, and we can note that there is a tetrahedral arrangement of atoms, and there is this kind of arrangement which is actually giving us an octahedron. So nice structures, seems quite complex, but in fact they are not. And moreover, if we go to the problems, then usually you are not asked to differentiate between normal and inverse spinels, but what you are asked is to understand whether cation will occupy a tetrahedral or octahedral hole. For example, in 2002, oh, by the way, that's one of the first problems at the ICHO about those structures, but it is very, very easy. So let's see. A common positive electrode material in the environmentally something Spinel type lithium manganese 204. The Spinel structure comprises a matrix, and here we have a description that is a matrix of qubit closed packed oxide ions stabilized by lithium ions in tetrahedral sites and manganese ions in octahedral sites. That's actually all you need to know, because the question is to give the coordination numbers of the lithium ions and the manganese ions in the Spinel structure of lithium manganese 204. Just think about it. As I've stressed previously, when you read the problem, you should understand what is actually essential in this text, and you can definitely mark that lithium ions in tetrahedral sites, manganese ions in octahedral sites. That automatically translates into coordination number of 4 for lithium ions and coordination number of 6 for manganese ions. And that is as simple as it is. Again, let me remind you that some of the questions at the ICHO, they are actually school level questions, or let's state it in another way, the logic is so primitive that you can definitely answer it quite easily. It's only the way the question is formatted that might puzzle you. The amount of text given is also one of the obstacles. What you should do, focus on the hints given in the text like here, and then keep calm, read the question, answer as simply as possible. A nice example actually from the Korea. It's 2006, problem number 8, that's the proper Olympiad, and you are given a structure of inverse and normal. Actually, that doesn't matter again. So some unit is given here, but it is not the proper structure of Spinel. Anyway, you are giving some information about how the B and A type of anions, cations, how they occupy the sites. And though you see that the terminology actually quite changed. So sometimes it's called a site, but I think in the latest problems it is called a hole. And what is asked here, what percentage of available tetrahedral sites is occupied by either iron 2 plus or iron 3 plus? And this is a tricky question because it doesn't actually matter whether it is iron 2 plus or iron 3 plus. If you untackle the logic, it means that in one case it will be either normal Spinel or inverse Spinel. And in both cases it will be only one side as shown in this figure, one side where you have tetrahedral hole filled with an atom. And therefore it will be 1/8. I would give you the opportunity to think about this logic, but also please consider how beautiful this question is, because it is quite a tricky one. In a way, it's funny because the answer, like in mathematics, I think in mathematical Olympiads, you usually have beautiful answers. And that is the case where the answer is quite solid. It's beautiful. It's just 1/8, no matter which structure you have. The other question is important for us because now it brings us to the D-splitting. So the magnetit, you know that's magnetic material, has an inverse Spinel structure, and you are asked to draw the crystal field splitting pattern. Oh no, the terminology again changes a lot within these problems. Basically, you are asked to draw a diagram. Oh, by the way, here's the answer. Now you can read what is the official answer to the previous question, and now I'm going to skip to this diagram. And that is a usual diagram which may have many different names, but what it shows the splitting of d orbital energy levels. And because we know that this material is magnetic, then it actually implies that some of the electrons must be free, non-paired. Now let's go to another question. This is a kind of absurd question because now the very large part of this question, of the whole problem, was dedicated to such Spinel structures where you have two kind of ions and you are asked to draw the diagrams for them. And then you have to discuss and decide which kind of which kind of arrangements are taken by those ions. So for zinc, because it has 10 electrons, it doesn't matter how you fill them. Either you have this d-splitting characteristic for octahedral holes or d-splitting characteristic for tetrahedral holes. It doesn't matter. For cobalt 3+, it does, because when you have octahedral holes, you have 3 energy levels below, which you can nicely fit with 6 electrons in that cation. And as you can see, all the levels are filled. This is a complete level, therefore it is one of the most structures possible. And cobalt 3+ doesn't want to take tetrahedral holes. It will be in the octahedral. So that is the logic, and I think that we must go back to it and then talk about it again and again until you understand it completely. If you would like to train, I recommend that problems for solving, because then you have much more examples. And let's just stress, now you have the proper tetrahedron splitting diagram, but it was also stated in the text that manganese 2+ in such structures is in tetrahedral. Moreover, you can see that if we put on each level 1 electron, so you have half field level and you have half field level, which is good. And then for nickel 2+, the octahedral splitting diagram is preferred because you have one completely field level and then half field level, which is also great. And for cobalt 3+, we have already taken that example. You have completely filled lower level, which is great. Now let's go to some other minerals, and I'm not going to frighten you, but I'm just saying that there are many different structures, including like oxides, and there was one problem about cuprites, but I don't want to just go into that because it's not in the preparatory problems. And there are, of course, silicates. What we should now stress about all these structures is that within all this polyhedral, you can have basically 2-3 environments where you could put your cations. It is tetrahedral hole, octahedral hole, or cubic hole. Doesn't matter how complex the whole structure is. You just focus on these 3 types of environment. And then we can go into ICHO 2021, which is also a bit insane because you would need to do a lot of calculation. And at that point, let me give you kind of recommendation that I'm giving you this very powerful idea that you don't need to solve all the questions one by another in a sequence. You actually can skip something. So this is A1, probably the first question in that problem. And you can see that although it is very easy, calculate the difference between the crystal field stabilization energies for octahedral and tetrahedral holes. So that's not the topic of this year, but I'm just showing you an example. You're asked to calculate this delta CFSE in terms of some splitting parameter, which is delta O, for various ions. So what you have to do is at least 6 calculations and then taking the difference, which is quite, first of all, it's mathematical. Second, it is a kind of automatic, like a robot. You just need to calculate something one by one and then compare and make a conclusion. But as you can see, the answer that is actually rated, for which you are given points, is like this. For chromium, it should be 0.4 delta O. For cobalt 2 plus, it's something 0.3 delta O. And that is what the graders are expecting from you. Anyway, what you need to do is a lot of calculations. And this is not just comparing numbers. You have to draw the diagrams, fill in the electrons, think about it. And then do not make mistakes. Consider high spin, low spin configurations. And then finally getting those two numbers. And for manganese, it's 0. Now, this one you can get without calculations. Or you can get the numbers just from your head if you have already calculated them before. But if you don't, then you might spend a lot of time on getting these numbers. And there is a high probability that you will make a mistake while typing in some numbers into your calculator, or then redrawing these numbers from the calculator screen onto your paper. So let me go back to this powerful idea. Sometimes you don't need to solve each question in a sequence. You can skip a question. But where would you like to put a mark for yourself that you have skipped something? So now remember that you have the title sheet, which is very important part of your set of problems. On the title sheet, you can make marks for yourself. Which problem you would like to solve? Which problem you don't want to solve? Which problem is the most easy for you? And also, which point a question you have skipped and you would actually like to come back, or maybe you would like to check it. So remember to put marks on your title sheet. And this is a nice example. And I'm not going into the calculation details because this is not the topic of the year 2022. Anyway, it's a very good example of those splitting diagrams, and this is the whole problem dedicated to splitting of energy levels for ions in solid structures. Let's go to another type of solids, which is cyanidoferate structure. And well, if you would like to have some other names, it could be cyanoferrate or it could be iron cyanides. Quite many different names. And this is taken from the internet for rubidium manganese hexacyanoferrate. There are a lot of examples because those are also as spinels and perovskites, they are used in various applications in catalysis or electrochemistry. For instance, this particular one is used for probably sodium-ion battery, because you can see that the framework, the lattice doesn't change, but you can put here inside some cations, and by doing so you can store energy. Now there was one question 2015 about ferrates like this, and this is about Prussian blue. So you can draw, you don't need to draw the structure, but you can just write the equation here, and it contains how many atoms? I think it should be Oh, is it correct? No, I think this is not correct. Something is missing here because we have 4, 3, so we have 7 iron atoms. Aha, so we are missing some indexes here. We should have 4 iron atoms with 3 plus, and then we should have 3 iron atoms with 2 plus, and overall 18 cyano groups. The question is, how does the energy diagram look for iron 3 plus and iron 2 plus? And we will go back to that specific question about splitting. Let me know, just show you the answer for that as you can see in that structure here, all the atoms, doesn't matter which oxidation state they are in octahedral holes. And therefore the splitting diagrams, now you can remember that it looks like this: 3 levels below and 2 above. And then we start filling them with electrons. And just remember this rule of thumb that half filled levels are stable. There is a reason for that. One of the best explanations, which is actually true, there is a so-called exchange interaction here, which stabilize them when they fill the whole sublevel. So it contains 3 degenerate energy levels. And the same applies here, where you have 2 levels of the same energy, which is called degenerate, and then you put 2 electrons like this, and that is very stable. And you have heard about this also for pi elements, because there, for example, when we talk about ionization energies, nitrogen has a very high ionization energy, the first one, and that's because of the same effect, having a half-filled sub-energy level. And now we go to iron 2 plus, where you have 6d valence electrons. And how would you like to put them? Well, if you put them into this high spin configuration, then they would not be so happy. They are not half filled, no, completely filled. So you would prefer the low spin configuration, where you pair them together. And why don't they want to pair on top? This is explained usually because when you put 2 electrons on the same orbital, of course they are moving in the same space, so they are repelling each other more strongly. And that's why you would like to put that electron on top, where it is moving on another orbital, and therefore it doesn't repel so strongly with some other electrons like here. However, here you're actually pairing them, but you see you are taking electron from the upper level and putting it below, so the potential energy should be lower. And if you go into solving problems like this, you are usually just considering what is the stabilization energy if we consider this splitting parameter and the pairing energies. When we compare them, we can conclude whether it is low spin or high spin. What is important here that for cyanidoferates, when you have ferrum 2 plus, then the splitting parameter is quite large, and therefore, at least for iron 2 plus, this configuration with completely filled sublevel is preferred. So that is the answer. Just for a moment, enjoy how beautiful those diagrams is, how fundamentally easy logic is presented. Half filled levels, stable configuration. Completely filled levels, also stable configuration. And that is exactly what is expected from you. And now you can sense this sense of kind of humor in all these ICHO problems. You rarely get an ugly answer. And if it is somewhat asymmetrical, like in this case here, now let's go to magnetit. Then there is a reason, because you know that is a magnetic material. That is what it is in the nature. So you have already a hint in the problem that is not going to be completely filled, but it has a high spin configuration, and that is the mechanism for magnetism. Now let's go to the last slide, and I think from that one we should go to the specific problem number 3 from the preparatory problem set 2022. Thank you for your attention.